So this was the secret formula that I gave you yesterday for taking a wire, taking a magnet, and making electricity. You know that you can have these two things and not have electricity. Having a magnet and a wire will not give you electricity. You got to have motion. Okay, so here's motion. Do I have electricity? No. Okay, it's not just any motion. It's got to be the right kind of motion. And what we really want to look at closely today is what does this kind of motion, what does it do to the electricity? How does it affect the flow? You saw it yesterday when I used this guy with the meter and I moved the magnet in and out. You saw that the flow did what? Changed what? Direction. And that's why it's called alternating current, because it alternates from going positive to negative. I'll give you the full definition here in a little bit. But what we've done now at this point, we trace back our understanding of this. It went back to Hans Oersted, who did the experiment with a compass, and he proved the opposite of this. He proved that if you have electricity, you got a wire, and the electricity is moving through the wire, it makes magnetism. So electricity plus motion of electricity plus wire gives you magnetism. That was Oersted. Faraday said just the opposite. He's the one that did experiments with the magnet, with the wire, with motion, the magnet, the wire, and motion, and proved that it creates electricity. So it doesn't have to be a copper wire, by the way. It could be any conductor as long as it carries electricity. Head up, man. All right. So what I'm showing you here now is a real generator. It probably is obvious to you that it's not the most practical idea to be doing this. In and out, up and down. That's a lot of wasted energy. Every time I move the wire down, I have to stop, and then I have to go the other direction, and I have to stop again. I keep slowing down and speeding up. I keep stopping in both directions. It's a lot of wasted energy. And we know that there are generators out there that are a lot easier. They work by going in a circle. And the dynamo is one of the first generators. It is what we used to call generators, dynamos. In fact, today when we say that person's a real dynamo, we mean they're full of energy. And that term goes back to Nikola Tesla. Remember how he worked on the dynamo for Edison and he came up with several designs? And you should be able to look at that and by that picture alone, because I'm going to show a number of diagrams like this today. By that picture alone, you should be able to figure out how that thing works. Can anyone describe it? How that works? Nathan?
The center thing is a magnet and it spins. Yeah, and there's like a conductor on the outside and on the plates, and it runs through that.
A conductor here?
Yeah.
Actually, no.
Or that's a that brings it into the little coil.
Okay.
There, and then the coil produces electricity.
Okay. That's actually even more detailed than what I was looking for. Excellent. So first of all, you have to identify the north and south poles on this magnet. It isn't here and here. It's one above and one below. And you can see that this wheel, I'm going to spin this wheel, and this whole thing will spin. And as it spins, those lines of force that stick off here, okay, they're going to be cutting through the wire. Or better yet, I could say the wires cutting through the lines of force. It doesn't matter whether I take the magnet and move it in and out, or if I move the wire. Either way, I'm going to break the lines of force, and electricity is going to flow through the wire, through the bulb, and back. This is an example of how a dynamo was used, well, not that long ago. When I was little and I had my bike, I wanted to have a headlight so I could go riding at night. And yeah, you could buy headlights that took batteries, but they didn't work that well. The batteries would leak and wear out, and they were costly. Nice thing about the dynamo is you'd attach this thing to the frame of your bike, and you'd go out for your ride. And as you were pedaling away, okay, you would be turning this little wheel, this wheel here, turning the magnet, breaking the lines of force. You can see that makes a lot more sense. Makes a lot more sense. Oh, I just broke the bulb. to go in this direction in a circle than it does to do this, up and down, okay? So all I've done now, I've taken the same basic design we talked about yesterday, going up and down, but now I take my loop, and here's my coil, and I'm going to put a little turn in it like so. So I've got a handle that I can crank. So now I take this, and I can crank the handle. And my loop turns in a circle. And I put that circle in the magnet, and I'm going to break the lines of force. Do you see that? Much more practical than going up and down. That's the beginnings of a basic generator. So we're doing this motion. I can take the end of this and I can attach this crank to a wheel and have water going over the top of it to spin it with water, have a little hamster running in a circle, I don't care, whatever. You can attach it to a gear, to a big propeller that turns with the wind, but we're using mechanical energy to turn this thing. And that wire is now breaking through the lines of force. So that's what we see here in this dynamo. So the difficulty with the dynamo is, I'll let you be me. You're cranking the handle, you're pedaling away. You're riding your bike, not too fast. You're riding your bike, cruising along, everything's going fine, right? And then you see a car and you're like, oh, they're going to hit me. I better stop. So you stop, and what happens?
But the wheel would still turn, wouldn't it?
Not if you're stopping.
Yeah.
Whether it's on the front or the back wheel, you're stopping. The wheels stop. What happens? Light goes out. At the very time you kind of need light. Now they can't see you. So not the best design. Plus, I can tell you this. When you go from cranking it, and now you turn that off. Keep cranking. Super easy. Okay? See how much easier it is? Because we're not using that energy to make... Do we have electricity flowing?
Yeah.
Yes or no?
Yes.
No.
No.
We can't have electricity because we don't have a circuit. Crank it. Is it easy?
Yeah.
Okay, I put it back on here and you feel the difference right away. It gets a lot harder because now we're using that energy to make light and heat. I'll stop for a second. Predict, will it be easier or harder to crank if I were to just remove the bulb and attach the two wires together? First of all, do I have a circuit? Yes. Will electrons be flowing? Yes. If they're not going through the light bulb, they're just flowing through the wire. What work are they doing? What would they do? Well, yeah, I see that, but they have to be doing something because they're flowing. And so what we're doing is we're cranking a lot of electrons through that wire, and it's going to get crowded. And when it gets crowded, what happens? We're not making light, but we are going to make heat. Crank it. You feel the difference? That's a lot more work now to make heat. It takes a lot more energy. It takes a lot more current to run a stove, to do a curling iron. I take that off. Whoa, super easy.
Jump.
Super easy, right? Okay. I'll show you something else too that you might find interesting. We'll talk about this later. That's a generator, right? Check this out. I just turned it into a motor. A motor and a generator are basically the same thing. One, we crank and it gives us electricity. The other one, we give it electricity and it cranks. It turns the handle. Yes?
You charge up a battery for that?
Theoretically, yes. On this particular one, no. But yes, you could do that. And in fact, some of you might have seen dynamos. They are coming back. We are seeing that kind of device used more in little gadgets around the house. Those flashlights you crank up, you've seen that before? Have you seen the flashlights that you shake and you see a little magnet move back and forth inside? Well, that's a generator, okay? And even though these aren't used any longer on bikes, generators are still the single way that we get electricity in our houses. You may be saying, oh no, that's not true. Because I know about the nuclear power plants. They don't use generators. Yes, they do. Yeah, but what about the hydroelectric plants, like Hoover Dam? They don't use generators. Yes, they do. Yeah, but what if you're getting your electricity from wind turbines? That's a generator, okay? So all those types of producing electricity all involves using a magnet and a wire and motion. So we have a generator. In some cases, that wire is turned by water going over a wheel. In some cases, that wire is turned by steam going through a pipe. We have our nuclear reactor, heats water, water makes steam, steam turns the wheel. Do you see? It all has to be mechanical, this motion. Okay, now that leads us to our first problem here. You look at this design, which is similar to what you see up here. You've got your magnet, you've got your coil turning, right, in those lines of force. Do I really have electricity with this wire the way it is? No, because they're not connected. There's nothing hooked to it. So imagine now that I had my radio, my wires of my radio going off, and here's my radio sitting over here on the table. And I'm going to crank this handle. What do you predict is going to happen? What's going to be the problem with this design? These wires go off to the radio, and I'm cranking the handle to make electricity. The wires are going to get twisted up, exactly. They go to something that's sitting here. It's not going to be spinning with this, it's just going to sit there. And as I crank the handle, these wires are all going to get twisted up. So you have to come up with a way of cranking the handle, turning the coil without letting the wires get twisted up. And the solution is right in front of you. Take a look at that as I pass out the assignment today and see if you can't figure out how that functions. You already know? Yeah. Okay. Hold tight and I'll let you explain it to everyone else. Mm-hmm. No. You have a cool class? Not very. You can trade it for one over there if there's no chart. Sky, you can move up one seat if you like. You can see better. I don't know if it makes a difference, but okay. All right, Nathan, why don't you come up and talk us through this? Tell us how it works.
I think
You can draw on it if you like.
Okay. I think this right here is like spinning, and then the electricity will come through here and down through here, and these are stationary, and it'll go up here and
Okay.
like the thing.
And then from there to where?
So,
Okay.
do that.
Sort of. Let's see if we can break this down. Thank you. I'll erase this so we can see what we started with. All right. First of all, when you look at a diagram like this of a machine, some of you are skilled at it. You're used to looking at these kinds of things, and others are not. So let me tell you what moves and what doesn't move. As you crank this green handle, you're spinning this rod that goes all the way through here. All the rest of this part here and here and here, is all stationary. It doesn't move. Okay? That rod is going to support your coil. The coil, one side of it goes down through these two copper rings and connects. This one on this side connects to the ring right here. Do you see that point? The one that on the other side connects to contact B, this ring. The part that might not be so obvious to you if you haven't seen this type of machine before is right here. This is the secret in solving that problem that I just brought up. These little black things here. They are actually conductors of electricity. Even though they're black, they do conduct electricity. And you can see that there's a wire going into one here and a wire going into the other one. Those are what we call brushes. Every motor, every generator will have something like that. Well, I should say every, most. They're called brushes. And you can see what that does is it solves the problem. Here is my coil of wire on this particular electromagnet, right here. Okay? And this could be a motor, it could be a generator. If the wires that went to this coil just came straight out here, as I spin that, they would get all twisted up. Instead, I make my connection to that coil right here. And each of those things connect to the coil through a little contact right here we call the brushes. You'll see that on every motor. I have a little RC radio control motor here. And right in here, inside, there are brushes so that I can spin this, or I could spin the motor, and the wires would stay connected here and wouldn't get all tangled. If you've seen those like slot cars, you know, you take these little cars and you put them on a track, and it gets electricity from the track, and the car has to be able to move along the track, and it has these two little pieces of copper that hang down and brush up against the track. Does anyone know what I'm talking about? That's the same idea. Those are brushes. It allows the object to move. It allows these rings to spin and still maintain a connection. So the wire that goes in here is connected to that black thing that I colored in blue. And that's going to press up against the ring. And the ring can now spin and be free to go all the way around as many times as it wants and still maintain a connection. How many understand what I just explained? Okay, so is that sort of, or you do understand? Okay, just want to be sure. Because I know that can get a little confusing if you've not seen that before. So picture this now as I'm cranking the handle. These rings are spinning and the connection is maintained by those two pieces you see there, the brushes. The first question there says to trace the flow through the circuit beginning at contact A. Well, here it is. I'll show you and then you can write it out. And you need to use the words. At contact A, that would be this ring right here. It connects on the inside right here and it runs down alongside that rod and connects to your coil, your loop. Okay? It could be a single loop of wire or it could be a whole coil like you see here spinning in there. Either way, we'll call it a coil. And then from there, it goes through here and connects to the inside of contact B. From contact B, it goes through the brush right here, through the wire, through the meter to power the meter, through this wire, through a light bulb filament, back out, all the way back to contact A where it started. And the whole thing starts all over again. Do you now see the complete path, the loop, for the flow of electrons? And we can crank that handle and don't have to worry about the wires moving because this part stays put. This is the part that moves. So the answer is electricity flows from contact A to the coil, to contact B, to the meter, the galvanometer, and that is on your paper. From the galvanometer to the bulb, from the bulb back to contact A. Electricity flows from contact A to the coil, contact B, to the galvanometer, to the bulb, and back to contact A. You can look up there. I've numbered it for you. Now, I told you yesterday that it doesn't matter whether we have this kind of generator, this kind where it turns in there, or if we have this kind where the wire goes in and out. I mean, the magnet goes in and out of the coil. All of those are going to create an electricity that will flow positive, net zero, negative zero. It'll be going back and forth. That's what's referred to as alternating current. Your definition for alternating current. Electricity that flows positive and negative created by a generator. Electricity that flows positive and negative created by a generator. That's why it's called alternating. It alternates. It goes back and forth from being positive to negative. Electricity that flows positive and negative and is created by a generator. It alternates. So if you saw me turn this handle, crank this handle, you would see the meter go up, reach a peak here, go back down to 0, and then it would start flowing the other way. This way, reach a peak, and go back to 0. The needle will be doing this as you crank the handle. Is that what you saw when you hooked up your battery to the galvanometer? No, it went up. And as the battery began to die, it went down. Once it reached 0, did it then start to go the other direction? No. If that were going to happen, that means your battery suddenly came back to life. Doesn't work that way, okay? It goes positive, and that's it. It flows in one direction. We call that kind of current what? Direct current. And we're going to get to that next week, so don't worry about that yet. But I just wanted you to see that this is going to make current that goes positive and negative. Now, yesterday, hopefully it was pretty obvious about why it went positive and negative. Why did it go positive and negative here? Yeah, because I'm changing the direction of the magnet, that I'm moving the magnet. So the direction I'm moving this matters, yes? Does the pole matter? Will the pole change the direction it goes first? Yes. Now it goes left, right, left, right. This time it went right, left, right, left. So the pole is important. The direction is important. On this one, if going down makes the current go to the right, what do you think going up will do? Make it go left. So it's all about the direction you're going through the lines of force. Get it? That's the key thing here. Now, it gets a little more complicated when we take that and we now spin it in a circle. You may not see how we're changing directions. All you see is, well, it's going in the same direction. It's spinning in the same direction. Well, it's all relative. In order to see how the direction changes, we're going to take this diagram and we're going to simplify it, okay? We're still going to have a coil of wire and it's going to be spinning inside a magnet. In case you were wondering, no, we can't have a magnet with just a north pole and just a south pole. Let's just pretend that that's this horseshoe magnet. And we've just cut off the bottom. Got it? Okay, so we have north and south next to each other and they're attracted. The bottom's just not shown in that picture. In this picture, what I'm showing you is the path that this little loop of wire will take as I crank it, as I turn the handle. I'm going to go this way, okay? And you can see it's traveling in a circle. And if you follow the path of that wire, you can see how it's cutting through the lines of force, how the blue line cuts through the green lines. Do you see that? Do you also see that the angle changes? At different points, it's going to go through the lines at different angles. What you need to do in order to understand this is instead of treating this like one loop, like this, look at that loop and consider it two wires, the top part and the bottom part. Because when I take this and I'm doing this, it's the top part and the bottom part that are doing the cutting, that are cutting through the lines of force. This part out here isn't even in the magnetic field. It's not doing anything, this part out here. It's the top and the bottom that are doing the cutting. Do you see that? So now, look up here and imagine, we're just going to keep our eye on the top part of the wire. We're picturing this part right here. As we crank that handle in slow motion, this top part then goes down through the lines of force. Then it reaches the bottom, and then it starts to go up through the lines of force. Down through the lines of force, up through the lines of force. Well, that's why the current flows one way and then the other. How many understand that? Good, because that's the key thing here. Now let's take it a step further. If we go back to this meter, and you look at the reading on the meter, a lot of people get confused by the reading. If the meter is right here, positive, negative, or neutral? Positive. If it's right here, positive, negative, or neutral? Negative. If this is positive 4 and this is negative 4, which one's doing more work? Neither. They're the same, right? I mean, I can hit you on the right side of the head or I can hit you on the left side of the head. They're both going to hurt. It doesn't matter whether it comes from the right or the left. It doesn't matter if the stream flows this way or that way. It's still current. So this is still doing work, okay? But obviously, if I'm down here at positive 2, that's not as much current as positive 5. You still with me? This is more than this. I point that out because you guys are used to meters and readings that start here at 0 and only go positive. For current, because it can flow left or right, we start here in the middle, okay? Left is still doing work, right is still doing work. This is doing a little less work, this is doing a little less still, this is doing none. This is doing a little work, this is doing a little more, this is doing the most. Does that make sense? Okay? Well, here's the reason why the current comes up gradually. When you hook up a battery, it goes from here, boom, and it hits that top. It doesn't rise slowly. It hits that top and it stays there. Okay? A battery works different. A generator makes electricity all along the way as it's doing its circle here. And depending upon the angle that it's going through the lines of force, it will give you more or less current. So here are 4 different situations. The blue line represents the path that the wire's taking. The green line represents what? Lines of force. Of those 4, which one do you think will generate the most electricity? 2. You said 2, you are right. If I ask you, of those 4 trajectories, paths, if that was my fist and this is your face, which one would do the most damage? Number 2. If I hit straight on like this, that's going to do a lot more damage. If I hit at an angle, it's not going to do nearly as much damage. This is your car driving into a concrete wall. This is more likely to kill you. This is less likely, okay? If you hit it at an angle. Does that make sense? So therefore, if we're going through like this, it takes more work to do that. Going through the strongest part of the magnetism, we're going to get more bang for our buck. We're going to get more electricity. Now, if I were to come over here, and I'll just label these A, B, C, D, which of those positions will this coil be in when we are generating the most current? Which of these match the most current over there? B goes with 2. 2 is the most current, and B is where that wire will be. As I'm cranking this handle and I'm turning that wire, it's going more and more downhill. Okay, here it's like right here. I'm not cutting through the lines very steeply. I'm going to get a little bit of current. Then I'm going to get a little bit more, and a little bit more, and a little bit more, until I reach this point where my wire now is going straight down. Boom. This end is going straight down, and I'm going to get the most current. And then here, I'll get more or less. Less, and less, and less, and less, until I reach this point. When I reach this point, it's like which one of these? 4. Now my wire is moving parallel to the lines of force, and how much current do I get? Nothing. When you're moving parallel, you're not breaking it. You get no current. Yes?
Can't you make a battery that can always be electricity? A battery that would always...
Well, battery's a whole nother ballgame.
Well, I mean, like, our circular magnet that would always make the electricity the highest it can be. Because if you cross them through like that.
Yes and no. There are ways to reduce this effect here. But whenever you're using a wire to go through lines of force and you're using the same pair of magnets and the same wire, you're going to always see this effect. You're going to see a rising and a falling. You can lessen that. You can make a different kind of generator, but that gets a little more complicated. I don't really want to get into it without confusing people today. Okay? So now we're at C. We're right here. We're moving parallel. That bottom part of the wire is going that way, and we're not getting any current. And then it was going down. Now it's going to go up through the lines of force, and we're going to make more and more current. Our max current is going to be at what position? A, D, D. It's going to be maximum here, because it'll be just like this, except the arrow will be pointing up. Okay? And then it will start to fall off more and more, and then it'll go back to 0 right at A. This picture here kind of shows you the different positions that coil can be in. Let's go ahead and answer number 2. We haven't already. As the device rotates, the current changes directions. Why and how do we know this? Why does the current change directions? We just showed it. What have we changed? We're still cranking the handle in the same direction. Why does the current change directions?
Because the wires, like, two things getting
Yeah, well, different angles, but I only showed, this only represents half a turn. The top of the wire is going down through the lines of force. What happens in the other half? It's not going down, it's going up through the lines of force. Do you see that? You pick a spot, this point right here. It's going down, 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 no current, up, up, up. So we get a positive flow, nothing, a negative flow, then nothing. We've changed the direction. I don't feel like you guys are getting this. How many think they understand that? Why we got a positive and a negative? Okay, didn't get you. Look at this one. Okay, this is the same setup. I've marked the end so you can keep track of what they're doing. This is the blue end, this is the green end. Do you see that over here, the blue end is going down through the lines of force? Yes? And we get current going to the right. As that continues in a circle, it's now going to go up through the lines of force. When it's going up through the lines of force, the current's going to go the other way. Down through the lines of force, up through the lines of force. Even though we're spinning it, we're still effectively doing that. We're changing the direction we're going through the lines of force. So that's how we get a positive and a negative flow. The end of the coil that was going down is now going up through the magnetic lines of force. That's number 2. The end of the coil that was going down is now going up through the magnetic lines of force. It's the same as moving that magnet in and out, or the wire up and down. The end of the coil that was going down is now going up through the magnetic lines of force. How do we know that, in fact, the current is flowing the other way? What shows us that? What's the proof? Right here. What shows us the direction the current is flowing? The meter. The galvanometer shows us this. That's the second part. The galvanometer shows us this. The galvanometer shows us this. Okay, I still feel like a lot of you are not getting this. You have to see the coil as 2 wires. This part and this part. One's going to go down through the lines of force. The other side is going to go up. We don't count the back side because the back side would be right here. And that is not going to break the lines of force at all. It's not even, they don't even go through right here, remember? They're in between the 2 poles, so this is where we find it. So if you think of that as 2 wires, then you'll see that when we're creating our circle, going around in a circle. This side is going to go down through the lines of force. Current will flow one way. The other side will be going up through the lines of force. Okay? When it reaches the bottom, then we start going up, and the current flows the other way. Incidentally, you might have put this together. Remember yesterday we figured out that taking a north pole and pushing it is the same as taking a south pole and pulling it. And that is why the other side is actually helping it do the same thing. Going up by the south pole is going to do the same work as going down by the north pole, which is why it flows this way. Okay? But as soon as that end reaches over here and starts going the other direction, our current flows the opposite way. Wes, you need to spit out your gum. Number 3. In what direction is the current flowing in illustration B and D? Well, you use the clock, in case you didn't know which way the clock goes, because you guys are so used to digital. Okay, this is clockwise. So what direction is it flowing in B? Counterclockwise. What direction is it flowing in D? Clockwise. Current is flowing counterclockwise in B and clockwise in D. This same illustration, by the way, is on the back of this worksheet, so you can always refer to that too if you didn't finish and you need to look at it later.
So D is clockwise?
B is counterclockwise, D is clockwise. Looking at the little blue arrows, that's your clue. Second part of that question says, why the difference? Why are B and D different? Why does one flow clockwise, the other one go counterclockwise? Please tell me someone knows the answer. Brianna?
Because the coil is turned.
Yeah, and what specifically? Nathan?
Because on one side it's going down from north, and on the other picture it's going up from south.
You got it. We're changing the direction. We're going through the lines of force. You guys still aren't getting this, are you? This is going down. You see that? See the yellow arrow telling me the direction we're going? This is going down. What's that side doing here? Going up. The difference in current flow is caused by the change in direction through the magnetic lines of force. The difference in current flow is caused by the change in direction through the magnetic lines of force. Even though the handle continues to crank in one direction, that one side starts by going down and ends by going up. The difference is in current flow is caused by the change in direction through the lines of force. Number 4, how often does the current reverse directions with each complete turn? Who can answer that one? Sky? Once. The current reverses once with each turn. The current reverses once with each turn. The current reverses once with each turn. And again, people get confused. They confuse the difference between the direction that it's flowing and the number of times it changes. Okay, everything that's up here, all of this is all positive. And all of this is all negative. So even though the needle may be moving from here to here, it's still in the plus zone. It's not moving negative. It doesn't move negative until it crosses 0. And then it becomes negative. This is just less negative. This is more negative. This is more positive, less positive. But every time we crank that handle one time, you're going to see the meter do this. Go here, here, and here. It went positive and then negative. It crossed the line one time. Every time it crosses the line, that's a change in direction. Okay? Every time it crosses 0, we say it's changed directions. All right, next question, number 5. Why is the light bulb unaffected by the change in the current's direction? Here you can see light bulbs on, and currents flowing in opposite direction. Why is it still light? Zach?
Because there's still electricity going through it.
Yeah, again, this is just like I hit you on the right side of the head, I hit you on the left side of the head. They're both going to hurt. We still have electrons. They're still flowing. Current is still flowing and doing work is the answer to number 5. Current is still flowing and doing work. Now I said it doesn't matter what direction the current flows. It doesn't matter to a light bulb. There are some devices that do care about the direction. And we'll talk about them later on. But for a light bulb or the meter, it's going to work. Current is still flowing and doing work. Number 6, there's 2 parts to it. What happens in illustration C? Why do we have no current? Because we're not breaking the lines of force. There's no reading here, no current. At that moment in time, even though the wheel is still turning, the coil is still turning, at that moment in time, the top and the bottom aren't going through lines of force. Andrew, the top and the bottom are not going through lines of force, and we get nothing. No current is generated because we are not breaking the magnetic lines of force.